So welcome again to another beautiful JEE problem. This again is taken from one of the previous JEE papers. Uh, Again, this is a lecture which has extended a bit more than I had intended. Now, if you are someone who understands, who is okay with the basics of physics, what I'll suggest is you can jump to, I think, around 12 to 13 minutes. The point would be given in the timestamp where the actual solution starts. But if you are someone who is still not very okay with the basics of physics, then you should actually go through the first 10 to 15 minutes of this lecture. Try to understand the formulas that I am suggesting, because the good thing about this problem is that there is a family of problems like these, and this is how these kind of problems are solved. So if you understand this lecture well, you will be able to do lot of such problems. So that's why this lecture becomes very important. So please be patient and bear with me for the next half an hour. uh, I promise you that there will be a lot of new stuff that you'll learn. So let's start. A thin rod of length L and uniform cross section is pivoted at its lowest point P inside a stationary homogeneous and non-viscous liquid. So slowly we'll go through the problem and try to understand what is happening. So in the first line, what they are saying is there's a thin rod of length L. Okay, so this is a thin rod of length L and uniform cross section area pivoted at the lowest point P. Okay, in a liquid, that liquid is stationary, it's homogeneous, it's non-viscous. Okay, fine. Non-viscous liquid implies that in very simple terms will have minimal resistance. So that is what is happening. The rod is free to rotate in a vertical plane about a horizontal axis passing through P. So let's try to understand this. So this rod is free to rotate in a vertical plane. So this is a vertical plane about a horizontal axis. So for example, this is an axis. So this is an axis, yeah, and this rod is free to rotate in a vertical plane about a horizontal axis passing through P. So as you see this on your screen, so you can imagine that this axis is perpendicular to the screen and this rod can move vertically, so basically in the plane of the screen. I hope you are able to understand. So first line is okay, second line is okay. Density d1 of the material of the rod, so the rod has a density d1 is smaller than the density d2 of the liquid. So density of the liquid is d2. So D1 is less than D2. Okay. So the density of this material is less than the density of the water. So let us say we can imagine that this is a wooden stick and this is in water. So that's the simplest way I can put it. And let us assume that you have fixed the lower end, and this this is how this rod can move like the minute hands. Okay, so third line is also okay. The rod is displaced by a small angle theta. Okay, this angle theta is small from its equilibrium position and then released. So then it is released. Okay, show that the motion of the rod is simple harmonic and determine its angular frequency in terms of the given parameters. Okay, so in the fourth line, what is happening is that this wooden stick is displaced by an angle theta. Now it is critical to understand that it's a small angle theta. One thing that I need to discuss before I even start attempting the question is, please remember theta. Now remember that this is theta is in radians. Remember that. And whenever we are doing calculus, theta is in radians only, so we don't have to worry much. But just to specify, this theta is in radians. Whenever theta is in radians and theta is small, always remember what the question setter is trying to tell you. What he is trying to tell you is that sine theta would be equal to theta and cos theta would be equal to 1. I'll repeat. Whenever theta is small, theta is in radians, sin theta is equal to theta. Actually, I should be putting a sign like this. Sin theta is approximately equal to theta, and cos theta is approximately equal to 1. Now, I have a detailed lecture where I have explained this. I'll put the link also here. This is something that you please understand, because when we are dealing with the mathematics, this is something that we'll be using. Whenever I'll see sin theta, I'll put it as theta, and if there is a cos theta, I'll put it as 1. uh, and I won't be going into the details, because I have a separate lecture. You can have a look at the lecture. Okay, so using this line, so I hope you are able to understand the significance of this line, displaced by a small angle theta from its equilibrium position and then released. Show that the motion of the rod is simple harmonic, and determine its angular frequency in terms of the given parameters. Again, so in the fifth line, they are trying to what they are asking is ki, boss, you need to tell me whether uh, basically you need to show to me that this is a simple harmonic motion. Once you have shown that, find the angular frequency in terms of the given parameters. This is important. Given parameters, that you can, whatever equation you have should be in terms of the length L. You can use d1, you can use d2. So I think, yeah, these are the only things that we have. So in terms of the given parameters, you have to give the frequency of the SHM. So now let's start. There are few formulas that we need to understand. If you have any doubt in these formulas, I request you to get the basics first, uh, your basics sorted, because these are the formulas I'll take for granted that you understand. So the first equation that I'll be using is tau is equal to minus k theta. So what does this equation tell me? This equation is basically the equivalent of f is equal to minus kx in the angular motion. Uh, I'll just introduce a bit of. I'll just give you an idea, not in the detail. In linear motion, we understand that a restoring force can be given as minus kx. So, for example, this is a common equation that we understand when we are understanding the spring system. In a spring, if this is a spring constant k, and I stretch it by I give it a small impetus of x, then the restoring force is in the opposite direction of force, and that is F is equal to minus kx. So you would have, this is a very simple equation. You would have learned this in the spring motion also. Now this is the linear part. This is the linear part. Its angular part is looks like this. So tau is equal to minus k theta. Why I'm introducing this equation is that when I'm analyzing the forces and I am able to show that the torque of the system, that the torque of this system can be put in the form of torque is equal to minus k theta, then I'll understand that uh, this wooden stick, which I've taken, I'll be using wood again and again. This wooden stick will be in a SHM, will be doing a SHM. If I'm able to prove that tau for the system, torque for the system, the restoring torque for the system can be put in the form of minus k theta, then I'll understand that I have shown that this is a SHM motion. So this is the first thing that I want to discuss. Second thing that I want to discuss is, second formula that I want to discuss is that tau is also given as I alpha. So again, F is equal to ma is something that we learn in I think seventh or eighth. So this is in the linear form. The angular form is F can, the equivalent of F in angular motion is tau, torque, and m is moment of inertia, and a is alpha. So I'll be using this formula. Third formula that I'll be using is that moment of inertia of a rod at one of its end. So if the pivot is this, then the moment of inertia can be given by 1 by 3 ml square, where m is the mass of the rod and L is the length of the rod. See, these are the formulas that I'll be using. I'm just giving you brief of these formulas. If you are not aware of these formulas, then please go back to your textbook and try to understand these formulas. So this is the formula I is equal to 1 by 3 ml square that I'll be using. Then see, what I'll be doing is that if I put the value of I as 1 by 3 ml square and the value of alpha is equal to d square theta by dt square, then I can also write the torque using this formula. So torque can be specified as 1 by 3 ml square into d square theta by dt square. Basically, this d square theta by dt square is the angular acceleration. Uh, uh, I'll spend 2 minutes about angular acceleration. See, in linear acceleration, we write it as a is equal to d square x by dt square. So a is a linear acceleration, but in terms of angular acceleration, we use alpha, and for d square x by dt square, we use d square theta by dt square. So this is the angular equivalent. I understand that if you know all these formula, you might be getting bored, but uh, that is a risk that I am taking. So okay, let's go ahead. Okay, then another thing that I'll be doing is, see, what I'll be doing is this d square theta. Okay, let me show you first. So in a SHM, when we are doing the spring chapter, sorry, I've written vice versa. So when we are doing the spring chapter, when we are doing SHM, the linear SHM equation that we get is d square x by dt square is equal to minus omega square x. For the angular, in terms of, let me call this linear. So the angular equivalent would be d square theta by dt square is equal to minus omega square theta. This is another equation that I'll be using when I'm doing the solution. So these are, you should be comfortable in using all these equations before you even start doing the question. So this is a setup that we have, and now we'll start looking at the solution. Okay, so let's look at the solution. Now see, this is what is happening. The mass of the rod that I have, that can be put in terms of d1 al. So what is d1? D1 is the density of the rod. A into L is the volume of the rod. So A into L is the volume of the rod. So volume into density is the mass of the rod. If I multiply the mass by G, then I have weight of the rod. This weight of the rod mg can be written as d1 al into G. Simple. This expression d2 alg, this is basically equal to the weight of the volume of liquid that the rod will displace. So that is why al is the volume of the rod, multiply that by d2. D2 is the density of the liquid displaced multiplied by G. So the first thing that I've calculated is the weight of the rod. The second thing that I've calculated is the buoyant force of the rod, because these are the only two forces which are acting. And where are they acting? Where are they acting? Let's try to understand that. So the buoyant force and the weight of the rod would be acting at the center of mass of the rod. So if this is the point X, which is the middle of the rod, then the buoyant force is in the upward direction, and the weight is in the downward forces. These are only two forces which are acting on the center of mass of the rod. Okay. Now we'll have to look at the geometry of the problem. Why we need to look at the geometry of the problem? Because we will be calculating the moment of these two forces about the point P. one, the buoyant force is in the upward direction, it will be trying to, the force would be, the moment of force would be in the anti-clockwise direction, and the weight of the rod is in the downward direction. So the moment of force of due to the weight would be in the clockwise direction. So one is in the buoyant force is in the anti-clockwise direction, and the weight of the rod is in the clockwise direction. Difference of these two movement of forces would be giving us the net torque on the on the rod. So for calculating that, basically what I need to calculate is the this distance xy. So let me zoom in. Yeah, so this distance xy, how do I calculate the distance xy? I take the pxy triangle pxy. In triangle PXY, sine theta is equal to perpendicular, this perpendicular XY, uh, I'm sorry, this perpendicular XY upon the hypotenuse. The hypotenuse is L by 2. Why L by 2? Because it is the distance of the pivot from the center of mass, which is half the length. So that is why XY would be L by 2 sine theta. So if I have to calculate the torque due to the weight, the torque due to the weight would be mg multiplied by L by 2 sine theta. L by 2 sine theta. Why? Because L by 2 sine theta is this distance xy. P is the pivot. Remember, P is the pivot. P is the pivot. This P. I hope you can see this clearly now. Okay. So my net torque is equal to mg L by 2 sine theta minus Fb buoyant force multiplied by L by 2 sine theta. See here, what I have done is that the torque due to the weight, that I have taken positive, and the torque due to the buoyant force, that I have taken negative, and it doesn't matter. Don't worry, it won't matter. You'll understand that in 2 minutes. So now this value of mg, this value of m d1 al, I've put here d1 al. This is what I have taken from this part and put here. Then multiplied by g L by 2 sine theta minus the value of the buoyant force d2 alg. D2 alg I have taken from part 2, the second equation, and put it here, and this is L by 2 sine theta. Now this is a bit of mathematical uh, manipulation that you'll have to understand. So finally, if you manipulate, this is the final equation that you will get. You can understand. Yeah, there is a one critical thing that will happen here is that when sine theta is taken common, and because theta is small, and that is what I was trying to tell you initially, because theta is small, so sine theta I am replacing it by theta, and that theta is here. So this sine theta, which is common in both the terms, that will be taken out and replaced just by theta. So finally, when I have done all the tam jam, then finally I reduce my this torque to half g al square d2 minus d1 theta, and there is a negative sign outside. Now you'll understand the significance of this negative sign. See, d2 is greater than d1. This is positive, this is positive, this is positive, this is positive. The theta is positive. So d2 minus d2 minus d1 is positive. So whole of this is positive. Whole of this is positive. Due to this negative, this restoring torque wants to take the rod back to its equilibrium position, and this is what we wanted, that this torque uh, should be in the format of a restoring force, and that is what I was trying to tell you here, that now we have boiled down whole of the equation in terms of tau is equal to minus k theta. See, this whole of this term whole of this term is a constant multiplied by theta, which was the initial angular displacement that you are given. So this would be the restoring force. So that is why we have shown, this is how we have shown the first part of the equation, where they were asking us, that show that the motion of the rod is SHM. Now we have shown that the rod is following the SHM. This part, whole of this part is a constant. Whole of this part is a constant. Actually, I should be referring to this. So whole of this part is a constant, and therefore the torque is a restoring torque. So this is the first part I have done. Now in the second part, what I have to calculate is the, if you look at the problem again, show that the motion of the rod is SHM and determine its angular frequency in terms of the given parameters. Now I have to find the angular frequency, and again I will be using the the formulas that I have discussed before. Okay. So now I know that torque can be written in the form of I alpha. Alpha is the angular acceleration, d square theta by dt square, a moment of inertia, because this is the uh, for a rod, this is the formula that we usually remember, because this is usually that we use, but this is through the center of mass of a rod. This is 1 by 12 ml square, at least this is the formula I remember. But here we have to, the pivot is on one side of the rod, so that is why the formula for moment of inertia that we'll be using would be 1 by 3 ml square. 1 by 3 ml square. And because I don't know m, I'll have to put it in the form of d1 al. So that is what I have done here. Ml square, m I have replaced by d1 al, and that is why torque is equal to d1 al cube 3 d square theta by dt square. So this is my equation 1. Now finally I have come to this point where this is my first equation and this is my second equation, and now all I need to do is put these in front of each other, using 1 and 2, put these two in front of each other, and finally find the value of omega square, and omega square would be equal to 3 by 2 g d2 minus d1 theta d1 l, and therefore omega is equal to 3 d2 minus d1 g upon 2 d1 l. So this is my omega, because they are asking me, the frequency. So I can write that 2 pi f, I'll write it here. So I'll write 2 pi f is equal to 3 d2 minus d1 into g, sorry, into g, 2 d1l, 2 d1l. So my frequency would be equal to 1 by 2 pi. This is my final answer. So 3 d2 minus d1 g upon 2 d1l. So this is the frequency, and all these are the given parameters, because I have d2, I have d1, I have the length of the rod. So this would be my final answer. So I hope this was useful for you. I have taken actually more time than I had planned, and hope this was useful and you learned something new. So let's meet in the next lecture. Thanks a lot for watching, and best of luck.